What specific problem does the TextCAVs method aim to solve in the context of deep learning interpretability, particularly in healthcare scenarios?
The TextCAVs method aims to address the challenge of generating interpretable explanations for deep learning models in healthcare, where obtaining labeled data for concepts can be costly and time-consuming due to the need for expert clinical input. By utilizing only text labels or descriptions instead of image examples to create concept activation vectors, CAVs, TextCAVs significantly reduces the cost and effort associated with generating meaningful explanations. This method allows for the extraction of model sensitivity to specific concepts without requiring a probe dataset, thus facilitating the debugging of models by identifying biases, as demonstrated in the Mimic CXR dataset. Furthermore, TextCAVs provides a way to rank concepts based on their relevance to model predictions, enabling human experts to quickly test hypotheses and explore potential issues in model behavior. Overall, TextCAVs enhances interpretability in deep learning models, making them safer and more reliable for critical healthcare applications.
How does the proposed TextCAVs method work? Please illustrate the steps involved in creating concept activation vectors using this approach.
The TextCAVs method operates by leveraging a vision language model, SI, to create concept activation vectors, CAVs, without the need for image exemplars. First, two linear layers, H and G, are trained to convert features between the target model, phi, and the vision language model, psi, using a cycle loss that ensures consistency when converting features back to their original space. Once trained, the layer, H, is utilized to generate a concept vector in the activation space of the target model, using only a text label for the concept. To assess the model's sensitivity to a specific concept, the directional derivative is calculated, which allows for the extraction of gradients based solely on the model weights, without requiring image data. Finally, by ranking concepts based on their directional derivatives, TextCAVs can provide meaningful explanations and assist in debugging the model by identifying potential biases or unexpected features in its classifications.
Can you provide a simple and illustrative example to explain the inner workings of TextCAVs, including how text descriptions are converted to concept vectors?
TextCAVs operates by converting text descriptions of concepts into concept activation vectors, CAVs, that can be used to explain model behavior. For a given target model denoted as phi and a vision language model, psi, TextCAVs first trains a linear layer, H, to map text features from psi to the feature space of phi. This is achieved by utilizing a cycle loss that ensures the consistency of features when converted back to their original space. Once trained, TextCAVs can generate a concept vector using just the text label of the concept without needing image examples. For instance, if the text description is lung collapse, TextCAVs will produce a corresponding vector in the activation space of the model, phi, allowing for the assessment of the model's sensitivity to this concept through the calculation of the directional derivative. This process enables the identification of how strongly the model associates the concept with its predictions, facilitating interpretability and debugging.
What are the main theoretical or practical advantages of using TextCAVs over traditional concept activation vector methods that rely on probe datasets?
TextCAVs offer significant advantages over traditional concept activation vector CAV methods that rely on probe datasets. Firstly, TextCAVs eliminate the need for expensive and time-consuming collection of labeled image examples, as they utilize only text labels or descriptions to create concept activation vectors. This is particularly beneficial in medical domains where expert clinical input is required for labeling. Secondly, TextCAVs maintain inherent meaning in the CAVs derived from text descriptions, allowing for more interpretable and relevant explanations. Additionally, by using a multimodal model, TextCAVs can measure model sensitivity to concepts without requiring a separate probe dataset for each concept, streamlining the process of generating explanations. Lastly, TextCAVs have demonstrated their utility in debugging models by identifying dataset biases showcasing their practical application in enhancing model reliability.
How is the effectiveness of TextCAVs validated or tested in the experiments conducted on both the ImageNet and Mimic-XR datasets? What metrics or benchmarks are used to demonstrate its performance?
The effectiveness of TextCAVs is validated through experiments on both the ImageNet and Mimic-XR datasets by assessing its ability to produce meaningful explanations and detect biases in model behavior. In the ImageNet experiments, TextCAVs achieved third place in the Secure and Trustworthy Machine Learning Conference Interpretability competition, successfully identifying all 4 secret Trojans, which demonstrates its potential for interactive debugging. For the Mimic-XR dataset, the Concept Relevance Score, CRS, is employed as a quantitative metric, indicating the proportion of top concepts related to specific classes. The results show a significant difference in CRS values between standard and biased models, with the biased model exhibiting a low CRS for atelectasis, suggesting that TextCAVs can effectively reveal dataset bias. Additionally, the analysis of the top sentences with the highest directional derivatives further illustrates the model's sensitivity to class-related concepts, reinforcing the utility of TextCAVs in model interpretability.
What limitations or potential drawbacks does the TextCAVs method have, particularly in terms of its applicability or quality of explanations, as indicated by the results from your experiments?
The TextCAVs method has several limitations, particularly regarding the quality of explanations it generates. In the experiments, some sentences produced by TextCAVs were not clearly linked to the respective classes, indicating that the model may rely on unexpected features for classification. This noise in the explanations could stem from various factors, including imperfections in the feature conversion between the target model and the clip model, or inherent noise in the gradient vectors. Additionally, the Concept Relevance Score, CRS, for the biased model showed a significant lack of relevant concepts for the class of atelectasis, with only 0.04, indicating that the top explanations were largely unrelated to the class itself. This suggests that while TextCAVs can detect dataset bias, the quality and relevance of the explanations may be compromised, limiting their effectiveness in providing clear insights into model behavior.